Hello, this is the next video in a playlist that I'm calling Probability Measure, and here we're going to look at examples with distribution functions on Rn space. So example 1, let f be a function from R2 to R such that R is right continuous and increasing in each coordinate separately. Give examples where f is not a distribution function on R2 space. So first one, if we let f of x equal 1, if x plus y is greater or equal to 0, and 0 if x plus y is less than 0. And let's let the 2 points, a and b, be this. First component 0, minus 1, and then 1 minus 0. So then let's calculate this measure. Remember, and this is if you look at my previous video called Distribution Functions in Rn space, then we discuss what this difference operator is. And it's the video just before this in the playlist Probability Measure. So we look at the difference in the second components and then the first components. And then we showed that this double difference operator equals this. Now if we plug in the values for B1, B2, A1, B2, etc., we get this. And now if we plug it into the function, so this is greater than or equal to 0, so it's a 1. So this greater than or equal to 0, so it's a 1, but it's a minus. And then it's minus, and then this 1 and minus 1 is 0, so that's a 1. And 0 and minus 1, that's a 0, right? And this is minus 1. So even though we can show that each component is a distribution function in one space, their corresponding distribution function in two space is not a distribution function, right? It's not increasing. So a second example, if we let f of x, y, we're in two space again, equal the max of x and y, and we let the points a and b be this, 0, 1, and 1, 1, then we look at this measure, f of ab, where, of course, a, b this is the right semiclosed interval, and the measure is this. So following, this formula up here, we get these values, and then it's the maximum of those. So it's a 1, minus 1, minus 1, plus 0, and it's minus 1. So this function is not increasing. Even though their marginal distribution functions are really distribution functions, their joint function is not a distribution function. So a third example, let's let f of xy equal the floor of x plus y, right? So the brackets is the floor function. So it's the largest integer less than or equal to this value. So if we let the points be 0, minus 1.1, and b is minus 1.9 and 2, then the measure, of course, we plug in the right values, and then we calculate the floor of each, and it's minus 1. So this is not an increasing function in two space, even though the floor function is a distribution function in one space. So now here, example 2, a distribution function on R is increasing and has countably many discontinuity points. Is this true for distribution functions on Rn space, for n greater than 1? And the quick answer is no. So let's let f1 and f2, let them be distribution functions on the reals, where f1 has discontinuities at x1, has a discontinuity at x1. Now let f of xy be the product of these two distribution functions, then f is discontinuous at x0, y, whenever x, 2 is greater than or equal to 0. Now notice that y it has an infinite number of values. So, this is an uncountably infinite number of points that it is discontinuous at. So it doesn't have to be countably infinite, or have countably many discontinuity points. So example 3, let f and g be distribution functions on Rn space, and let AB be a right semiclosed interval in N space, Rn, where A and B are vectors in Rn, and A is less than or equal to B. Now, as a reminder, that f of this right semiclosed interval is the difference. We use the difference operator on every component, so all n component. So there's n differences here, and we showed what that was in the previous video. Now, if f of AB is equal to g of AB, where these are both distribution functions in n space, and they equal for all A and B, are f and g equal up to an additive constant, right? That's a common question, and the answer is they don't have to be, right? So let f and g be arbitrary functions. Now remember, this is not capital F or capital G, it's little f and g. So they're just functions from the reals to the reals. And if we let the distribution function f of x, y, z just be f of x, g of y, and then let capital G just equal 0 for all values, then notice it's increasing, right? Because it's greater than or equal to 0 for all x, y, and z. Now then, the measure f of AB, right, is equal to the measure of g of AB, right? Because this is a difference operator in every component. But since that third component can free range, the difference of that third component ends up being 0. And I'll let you go through that as a homework assignment. And so this measure is 0. And this is always 0. But look at this. The functions don't equal, and they're not a constant. One's not a constant of the other. So they don't have to be, even though they equal for all A and B, they don't have to be a constant, equal up to an additive constant. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.